My name is Rich Jones. I'm going to tell you everything you need to know about longitudinal data analysis in 1 hour. First, let's start with other resources. My favorite book on longitudinal data analysis is a book called Longitudinal Data Analysis. Applied Longitudinal Data Analysis, sorry. And it was written by Judy Singer and John Willett. Great book. Taught me everything I need to know about doing longitudinal data analysis. Variety of different frameworks, variety of different types of outcome variables. Go out and get this book. Then, go over to the IDRE website, which stands for something important at UCLA. Used to be the Academic Technology Services website. And if you click this link, you'll get to the examples in the ALDA book. Applied Longitudinal Data Analysis is at the end of that URL. So all the examples in the book have been worked out for you in SPSS, SAS, Stata, R, and Mplus. And so if you're trying to learn how to do something in R, for example, and you finally figure out how to get your data into R and you want to know if you're getting the right result, you can do it in SPSS, which you know, and then do the same example in R. You've got the code, you can compare the results. It's just a great way to learn how to do something new. If you want to know how to do longitudinal data analysis, specifically in a structural equation modeling framework, there's this great book by Jason Newsom, and it's called Longitudinal Data Analysis, and it's specifically written for researchers in aging. And there's a book by the Duncans on an introduction to latent growth curve modeling. It's a little more general for psychological researchers. And so here's a book, 2013 by Merman, and it's called Growth Curve Analysis and Visualization Using R. So I found this book preparing these slides because I'm trying to learn R. I wanted to have a nice R book to recommend, and the reason why I'm going to recommend this book is because it's LME4 and ggplot2. And if you know R, you may know that those are important functions. LME4 is what we're going to use for mixed effect models, and ggplot2 is a really nice way for drawing figures. And there's about 6 different ways for drawing figures using R, so it's probably only useful to learn one of those. And some of the resources that you'll find out on the web may be older and not relevant to ggplot2. So now I've saved you a click. And here's a book that does R with ggplot2. And here's a really nice book from Alexander Bogin that's called Latent Variable Modeling Using R. And this is a textbook that's mostly about using R-Levon. And Levon is a package in R that was written to mimic Mplus. And so your lab leader won't buy you a copy of Mplus, and you can't convince them, and slashing tires didn't convince them. You can use R-Levon and do most of the things that you can do with Mplus. And this is a really nice book on using R-Levon. And it's a really nice book in general anyways, with nicely written examples and pretty pictures and nice explanations. And then if you like math, raise your hand if you like math. You can read this book by Bolen and Curran, which is full of complex equations and matrix algebra. Tells you all about doing the latent growth curve modeling, and it's really written for statisticians or statistician-minded people. And the other thing I would like to let you know about is I teach a 3-day workshop over the summer on how to do longitudinal data analysis using Mplus, and I've been doing it for like 16 years or so. And I do it usually in July, usually the end of July, in Providence, and I actually teach you how to use Mplus software, how to get the data in, how to read an input file, and how to interpret the output. And it's really meant for beginners, people who are just starting and getting an input file into Mplus. It assumes you know nothing about Mplus or latent variable modeling. And you can use the demo version on your own computer. You don't actually have to commit to a lifelong relationship with Mplus to attend the workshop and participate. It gives you a chance to test it out see if it might be useful for your purposes. But more importantly, my materials for that workshop are available online, and all you have to do is click that link right there in that file you don't have, and you can go right to my website. You can also search for it. It's called lvmworkshop.org, and go to the downloads page, and you can see all my slides that introduce Mplus, that introduce longitudinal data analysis using Mplus. There are examples there with example input files, example data files, real data, and you can do real analysis on that real data and get a real sense for what you can do with Mplus. You can follow along the slides and go through the text that describes the examples. But it's better to come and be there. Plus, we have snacks. And finally, on the Mplus website, which is statmodel.com, they keep a list of running workshops that you can look for and attend, and they're often very nice. But I used to go to Bent Mu 10's workshops often, and they're just fantastic. But what he covers is all the fabulous things you can do with Mplus and how great Mplus is, and doesn't actually show you how you do it, how you write an input file, how you do the data analysis, how you interpret the output. And so that's what I do over those three-day workshops. Tonight, I'm just going to give you a Bent Mu 10 style survey of all the cool things we can do with Mplus and longitudinal data analysis. So what's longitudinal data analysis? Longitudinal data analysis is analysis of data where you have observations on people that are repeated or replicated. Longitudinal data analysis is usually more interesting when you have more than 2 observations per person. Inside the tent of longitudinal data analysis, we can have outcomes that are absorbing events like mortality or dropout, or conversion to dementia, discrete but non-time absorbing like conversion to mild cognitive impairment. Some people get better, right? You can have outcomes that are quantitatively distributed like neuropsychological test performance, and quantities that are not directly observed but measured indirectly like latent variables, which is really cool for integrating measurement error in your longitudinal data analysis model. Here is a picture of what longitudinal data analysis looks like. Here's a data set of 2 people, person A and person B, and they're observed at 4 ages, and we have some outcome variable, a performance variable, and some metric for time. Here it's age, and the question is, how fast do people decline on performance with age? And how well are they performing at baseline? And are there potentially any individual difference factors that I can think of that help explain where people start and how fast people change? And our questions are all about answering that type of a model. And longitudinal data analysis is nothing more complicated than a linear regression. I'm going to regress performance on the time metric. And now I've got an equation over on the right-hand side. We're just doing linear regression, performance on time. Well, here's a more mathy version of the same figure. Let's call it y on x. So we're going to do a simple linear regression with an intercept and a slope on x, and let's x be the time metric here. What makes longitudinal data analysis unique and cool is we're going to introduce some special modeling features that account for the non-independence of observations, the fact that each one of those repeated observations of the performance variable over time aren't independent from one another. That violates one of the important assumptions of a linear model. So we'll use special models that can handle that non-independence in our estimation procedures. Typically, we'll have more than 2 people in our analysis. So here's an example where we've got about 20 different people that are followed over time, and their lines are shown in gray. And we make our inferences and what change looks like over time and where people start by talking about averages or means. What's the mean pace and change over time, and what's the mean starting level? And sometimes you'll hear these models referred to as mixed effect or random effects, And that just refers to the dispersion of people around this overall mean and average slope over time. So piece of cake. See? All you needed to know. Look, you like math? Here's math. This is, you can think of this as a multi-level modeling framework here. So here's our linear regression model. We've got an intercept and a slope over time, and we can look at how we might explain that intercept and slope by, again, regressing that intercept and slope on predictors, or here's just an intercept-only model, and we do special things to handle the non-independence of observations and people. Here's the same slide, but now I'm using the Greek that you'll find in your structural equation modeling software. So instead of B's, I'm going to use etas. Etas are latent variables. When we start doing this work in a latent variable modeling framework or structural equation modeling software, we switch to a different notational system, but it's the same model. And so here the slope is being represented, the random effect, that's the intercept, is being represented with a latent variable eta. And the same thing with the random slope. It's represented with a latent variable called eta. And finally, just to prove that symbols don't matter, when you pick up your Mplus user's guide, they call these factors I's and S's for intercepts and slopes. They're just names and labels, and it's the same model despite what we call these things. And I was asked this today in my work group, what are the advantages of doing your longitudinal data analysis? Why would I want to do this in Mplus? Why don't I just want to fit a model, a mixed effect model, and use interaction terms? And the answer is there are no advantages of doing your latent variable modeling in a structural equation modeling framework if you have a nice, simple, straightforward research design and research question. Who's got simple research questions and straightforward research designs? Okay, you're excused. So oftentimes it doesn't take long before research questions start to get complicated. And the structural equation modeling framework gives us tools we can use to try to model complications and design issues. But if you can do it with a traditional mixed effect model using your general purpose statistical software package, I highly recommend it. It'll speed up review. It'll make the results more accessible. I mean, it's a real art to try to explain and convey the methods that I use using structural equation modeling in a language that I think will be familiar to people who are trained in mixed effect models. And it's an art that continues to be honed over years and decades of work in this area. But even though you'll meet a lot of Mplusers here, there aren't that many outside of Lake Tahoe. So today, so when you want to get your papers reviewed, it sometimes can be hard. And it's harder in epidemiology and medicine than it is in psychology. In psychology, it may be no big deal, but as we're doing research in a lot of different areas, or you're doing AD research and publishing in AD journals, it's not all psychologists who are reviewing those papers. But if you have challenging design issues or complexity that's substantively important, say you really want to estimate a joint model, you want to look at change in simultaneous processes or sequential processes, you want to model a missing data mechanism, you want to look at subpopulations, or look at multi-level models, or say, for example, you want to include weights in a mixed effect model, easy to do with Mplus if your models converge, and you say you want to include a measurement model in your longitudinal data analysis model. Mplus or Levon is the place you want to be. Use promo code RNJMA when you buy your Mplus software. Just kidding. I get nothing. Okay, so here's my cartoon of the longitudinal data analysis modeling framework. We're going to be talking about observed variables, and those are going to be enclosed in squares. So I've got y's and u's. Y's I'm going to use to represent observed continuous dependent variables. U's would be observed categorical dependent variables. X's are going to be observed background variables, covariates, predictor variables. Latent variables are going to be enclosed in ovals. So we've got an F and a C in a box. The F is going to be a continuous latent variable. The C is going to be a categorical latent variable. And the C in a box is going to be a special type of categorical latent variable for doing multiple group modeling. And the I in a triangle is a constant term. It's a little convention that was used in longitudinal data analysis and structural equational modeling framework. So here's a path diagram of a simple linear model for change over time on an outcome variable that's observed 4 times in a structural equation modeling framework. It's a highly constrained confirmatory factor analysis. If you know factor analysis, you might be used to estimating factor loadings. In growth curve modeling, the factor loadings are fixed to values that are informed by the design of the study. They're not typically estimated. And, but we're interested in the means and variances of the intercept factor, the slope factor, their covariance, and we can introduce covariates into that model by adding a column of data that has covariate data and regress outcomes or growth factors on covariates and look at how variability in slopes and intercepts changes with a covariate. This model to this point is exactly the same as the SAS proc mixed model. And if you go to you'll have to go to my short course website to find this example in this slide. But this is the first example from the Applied Longitudinal Data Analysis book from Singer and Willett. And they give you on the ALDA website, at the IDRE website, code to do this example in SAS and SPSS. They don't give you Mplus, but I'll give you Mplus. But in my 3-day workshop, I show you that the results that we get using a simple growth curve model approach are exactly the same that you get if you did the same analysis in SAS proc mixed. And I think that's important because I want you all to understand that at the basis, these are the same as the mixed effect models that we estimate using SAS or LME4 or whatever your favorite tool is. And they only get different when they get special and handle special analysis problems.
Rich,
yeah.
So is this assuming the factor structure is constant across time, or is that also a variable where the factor loadings can be altered as a function of time?
So that sounds like you're interested in a multiple indicator latent growth curve model. So this is a picture of model for one variable that's changing over time. That one variable is y1, and it's also observed, that same variable is observed at a second time point and a third time point and a fourth time point. There's no factor structure over time here. There is a factor structure here. It's how the etas relate to the y's, but the structure of that loading matrix is determined by the design of the study. The factor loadings here are all constrained to 1, and the factor loadings here in this picture, they're constrained to 0 in y1, 1 in y2, 2 in y3, and 3 in y4. And those aren't estimated; those are fixed. And by putting constraints on the means of the y's, we force the information on the means of this variable to get pushed into the latent variable. And so the latent variable mean is the intercept value for this longitudinal series, and the mean of the eta2 variable is the average change per time point in the latent variable. And so there's no factor structure that's changing over time here. But we could do stuff like that, and that would be in a multiple indicator model. I'll have a picture of that. How about another question? So here's an example of a parallel process latent growth curve model. This came up in our work group today. We've got a group that's interested in looking how two things change over time. Oh, so here's one process called Y1, Y2, Y3. So here's 3 repeated observations. Here's another one labeled Y1, Y2, Y3. Maybe I should change these to like X1, X2, X3. That might be more helpful. But it's a
twin study.
It's a twin study. Thank you. So say we're interested to know how. So let's say you're interested in cognitive reserve and functional reserve. And so we want to look at how cognition changes over time and how function changes over time. We can look at those and we can see if those change factors are correlated or if there are shared predictors of change in those two things or other funky stuff. Here's the multiple indicator latent growth curve model. So now the outcome that's changing over time isn't one observation. It's not one cognitive test score. It's a latent variable, a factor that's measured by 3 different cognitive tests. 3 different cognitive tests at time 2, same 3 cognitive tests at time 3, same 3 cognitive tests at time 4. And so the factor structure for the measurement model for the latent variable is here, and this can be the same or different over time. You can test whether it's appropriate or helpful to allow that to be different over time. But we can still capture changes in that latent variable over time. These are very hard to estimate. Place a lot of demands. There's a lot of places where the estimation can go wrong here. There's a lot of correlations that need to be accounted for.
What if the factor structure differs over time?
You can look at you. So Dan asked, what happens if the factor structure changes over time? And if the factor structure changes over time, and you believe that the factor changes structure, you believe that it's actually different over time, then if you don't control for that, you could get a biased estimate of how fast people are declining or improving over time. And you can use this type of a framework to allow it to be different over time.
So can it be completely different?
Can it be completely different?
Depends on what you mean by that.
So can you have different intercepts and loadings at different times?
So you probably want to have something that's the same inside the measurement model over time. So if we had 3 different cognitive measures measured at time 1, time 2, and time 3, and at time 4 we had BMI, shoe size, and credit rating, that would have a different factor structure, it's different indicators, and it wouldn't be informative of the under. But if we had one of the cognitive tests and shoe size and credit rating, then maybe we could still use that to get some information about that latent variable, as long as we could assume that the relationship between that one test that's the same over all time points was the same test at the other time points. Maybe not exactly shoe size and credit score.
So you need at least partial invariance.
You would want to have partial invariance.
Do you mean, like, when you talk about partial invariance, do you mean, like, do you need at least one factor loading and one threshold or intercept for one of your variables to be the same, or all your factor loadings and none of the intercepts, or vice versa?
I think you probably just need one factor loading, one item with a common loading and common threshold. That's my guess. I don't actually do these types of models, but I think you could get away with just one. And so this, one way that might show up is if you have different tests over time. We're adding a new test to the battery after wave 3 because our other tests, we don't want to keep using them anymore. They were too easy. So that's a missing data problem, but it's also a different measurement model from wave 3 and on.
You had some tests that are, in a fairly standard kind of cognitive testing framework. You have something like vocabulary that's pretty resistant to change, and some other tests that are very sensitive. Then the relative relationship of those things might be altered over time.
Yeah, but so that example brings up what you might want to include in that factor. So if you think vocabulary is a hold test, that's probably not a good indicator to include in a model where you're trying to study change over time, because we would want. So there's one intercept and one slope, and this model assumes that this one slope is a good summary of the change in all of the tests that are being used to measure the latent variable. So if you have one variable in here that's not changing the same rate the other ones are changing, that's not a good. I wouldn't include that in this factor.
Simple example, if you have a verbal and a spatial factor or something, you want to look at both going over time, then you're really dealing with two latent variables.
Yeah, I would use the parallel process for that rather than multiple indicator. So this would be like for logical memory and some other story recall test, or another memory function, attention memory function test. You could put a whole battery in there, but I might not include a whole test like vocabulary knowledge in that factor score. We can control for practice and retest effects in a latent growth curve modeling framework. This often happens in cognitive aging research, and we do it just by adding in additional growth factors that have, it's like adding a second intercept to the model to capture a bump in performance between baseline and second follow-up. And we can look at how background variables might be related to intercept and slope, but also to magnitude of the retest or practice effect. Longitudinal data analysis in randomized controlled trials is a especially interesting application. And there's a nice paper by Muten and Karan that demonstrate that a multiple group approach to analyzing randomized controlled trials that views the treatment effect as not as a dummy variable effect, treatment versus control, but as additional latent change factor that's only exhibited in the intervention group and not shown in the control group, has been shown to be more powerful than ANCOVA analysis for RCTs. They use simulation studies. And you can look at crazy things, like if the treatment effect depends on baseline. Where's Maria? I heard that's her favorite thing to do. Here's a picture of doing a discrete time survival analysis. So when we do discrete time survival analysis is when you have a survival function, but we code that survival function with multiple different survived, died previously values in a column of data. So it'll be alive is 0, died is 1, and if you died in a previous time period, you'd have a missing value. We can estimate that type of a survival function in Mplus, and this is what the picture looks like. It looks complicated, but it's actually really easy to code up. I've got a new symbol here was a circle and a square. This is meant to represent missing data. So missing data is a real issue in survival analysis studies because once people die, they're missing on future values of the survivorship indicator. And it's well handled by Mplus with the right estimator, but complicates other types of models. And so we can include a model like this inside of a latent growth curve model, and now we've got a joint model. You can also do continuous time survival models, and that's shown in this picture. This is from a paper by McCardle. This was a joint model that has a growth curve model on the right-hand side and a survival model on the left-hand side. This was survival to time to Alzheimer's disease onset, looking at change in cognition over time. And that's a hot thing this year, hot thing to do this year, joint models. And if you have any data that might be causal of survival in your analysis, and maybe it's more important than we all thought. I would love to see how results from this type of a model correspond to what the Cecile's program in R that was released at Melodem or before this year, discussed at Melodem. So growth mixture modeling is a really fun application, and this is used to try to find population subgroups that may have different parameters that relate to change over time. And so mixture is a word that's used in these models, and it's unfortunate because it sounds like mixed. Mixed models refer to longitudinal data analysis models that have a mixture of fixed effects and random effects. Mixture models are models that are longitudinal data. Well, mixture models are any type of model that is a latent, categorical latent variable model, like a latent class model where the class indicators are continuous variables. So if you're doing a latent class analysis, you're trying to find latent classes, and the indicators of class membership are categorical variables. If your indicators of categorical latent variable membership are continuous, we say we're doing mixture models. And when we do growth mixture modeling, the indicators of unobserved class membership are continuous variables that are slope and intercept or other important parameters of change over time. So here I'm trying to say we may have a group of people having change over time, and there may be a group of people who are having faster change and another group that's having slower change or maybe no change over time. And maybe we want to try to see who's in which group. And this is the way I like to draw those path diagrams for those growth curve modelings, growth mixture models. I include a latent variable labeled C, so it's a categorical latent variable, and I've got an arrow pointing to a great big box that goes around the entire growth curve model inside, and that's meant to represent that we can allow membership in this unobserved latent class variable to be anything inside that model. It's typical to let it be the mean of the intercept and slope factors and their variances, but it could be anything. It could be a covariate effect on the growth curve parameters that defines who's getting in the latent class variable. And we can include predictors of class membership to try to see how do my different demographic variables predict membership in one of those growth model parameters. Or can I have covariates that just explain variability in the growth model parameters and explain variability in class membership? And this is a ridiculous model. I just show up, this is my cautionary tale. You must be very explicit in your hypothesis generating before you move into this type of modeling, because it's very easy to get on what I call the analysis merry-go-round, where you keep analyzing new and different variations of the same model and you're not really sure when you're done. So clear hypothesis formulation is really important. We did a growth curve modeling paper out of this workshop many, many years ago. Kate Hayden was the first author, and we used Ross map data and found 3 groups of people having different paces of cognitive change over time. And there was a class of people that had slow change over time, a group that had faster and even faster change over time. This slow change group was 65% of the sample over 12 years in the Ross study. So this was encouraging. This means that what? The normative expectation with aging is almost no cognitive change. That's good news, right? Well, it depends what line of business you're in. Say, for example, you're a cognitive aging researcher. But other than that, it's good news.
I think we should just stick with it's good news.
It's good news. Okay. We showed that there was of those people in those different classes, there was a slight difference in the distribution of neuropathology, offered some validation for that type of approach. So that's a fun thing to do. I'm off growth mixture modeling. I thought it was cool at the time, but now I'm off it. I think it's really only useful and interesting when you have a study design where there's a meaningful 0 point for time. Otherwise, this model is saying that there are some people who would have had cognitive performance scores, up around 3 standard deviations above the mean earlier in life, had we observed them, right? So this class membership is a cross-sectional summary of their longitudinal trends over 12 years. So I don't find this helpful or useful. But this picture does make you think about other types of cool models called change point models, where we're interested in what factors influence when a person moves from being in the slow decline class to the fast decline class. So that's you can do that with Mplus too, even though I don't know how to. So here's an example that actually got published. This was an example of doing a known class mixture model, which is a data trick to incorporate a post-baseline categorical mediator in a model of cognitive change over time. So we had a particular study design where we had a cohort of people who were enrolled in elective surgery, and we got a preoperative baseline cognitive assessment, and then we followed them in the recovery period in the hospital to see who got postoperative delirium, and then we related that postoperative delirium to retest effects, delayed retest effects, and the slope of cognitive change over 3 years of follow-up time. And the delirium outcome is not really covariate because it's dependent upon baseline cognitive function. Your risk of postoperative delirium is actually strongly influenced by your preoperative cognitive performance level. And so the way we included this post-baseline categorical outcome variable was to use the mixture modeling procedures in Mplus. But it's known class, which means we know who's in the class, but we're still using the mixture machinery in Mplus. I don't think you can do that with SAS-Proc Mix, but I bet Danielle Harvey could do it. But she's not here. So you can do your growth curve modeling in a multi-level modeling framework with Mplus. So you can estimate the same types of models we would do with latent growth curve modeling with a multi-level modeling framework. And Dan had some slides that look like this up yesterday. And this is really useful approach when you have high intensity longitudinal data, which sometimes means more than like 10 or 12 repeated observations. You can do Mplus with more than 10 or 12 repeated observations. It's just that you got to have another computer to do your other work on because those models will take a long time. Multi-level model is a little bit faster, but it reduces to the same analytic model. Another type of use would be if you want to look at change in like more than 2 outcomes. We did parallel process. We were looking at change in 2 outcomes over time, but what if we had 12 outcomes over time, like brain parameters from FreeSurfer, and you wanted to look at those changed over time, and you had scores of them? You would do a multi-level modeling framework. So Jack McArdle is responsible for another approach for longitudinal data analysis that's called latent difference score models. In this model, the change between 2 observed variables is captured with a latent variable. This is called the latent difference score. This is a different model than your SAS-Proc mixed model. And it's nothing more than change in the bivariate case with just one observation and one repeated observation. But when you have more repeated observations, we can look at change values from adjacent time points, and we can look at systematic differences in those change values over time. And this can be a really useful model for capturing unusual change patterns, nonlinear change patterns. The only downside is I've never been able to get any of these models to work for me, but Laura has. So if you have questions about these, ask Laura. Raise your hand, Laura. Say hi. Laura's got those models to work. So here's the picture. This is from Preacher and Hancock, 2015. Really nice paper on scolding us for using linear models as a default to look at change over time. And so in this paper, they go through many different types of alternative parameterizations for the time effect to capture nonlinear change patterns. And one of those is a random change point model. And if you can figure out how to read that paper, and they do supply code, you too can estimate a random change point model. And Doug's done this. Doug, raise your hand. Doug has done this for us, and so it's a really neat trick. The caveat is sometimes if you have individually varying time points of observations, there are flavors of Mplus longitudinal data analysis that can accommodate that type of data. We don't have to assume that everybody was seen at the same time. And that's a development that came out after the Mplus first came out. It's kind of unique to Mplus among structural equation modeling software packages. The ability to handle those non-uniform time points of observation. This framework for doing the random change point models doesn't accommodate individually varying time points of observation. So if you have that, you're going to have to do some additional data managing to make sure when you put observations in columns that they're in relatively homogeneously spaced time points. So that's the only caveat for that type of analysis.
Otherwise, it's straightforward.
I mean, look at it.
Yeah.
Do you want me to leave that up so you can copy it down more? You got it?
There.
So it's all in how many different time points, how many different factors you have to incorporate the time, how you scale those time points. It's pretty elegant, but.
Is that a square root sign up there, Rich? Yep.
Yes.
That scares some.
Yeah.
It's all in the model constraints part of the device.
So now this is crazy, and this is my own idea, and this was my own crazy idea last time I gave this talk in 2012 here at Friday Harbor. This is a crazy idea to try to think about how we can use neuropsych data and other data to try to do a better job of making our classifications of people. So what's in here? First of all, I've got a test like the AVLT, which is a word list learning and memory test. There's usually 5 learning trials of a 15-item word list. And so these variables here would be the number of words recalled after being presented with a 15-item list, and presented again with the list before each time period. And then there's 3 tasks that follow that administration, which is a this would be the interference performance task. This would be the recognition task or recall task, and then one would be a delayed recall task, right? Short delay. There's an interference task, there's a recognition task, and a delayed recall task. Why I chose B, I don't know.
That's list B.
That's list B, yeah.
Should be A
Good.
6.
That's why. Okay, so so this is our complex. There's a lot of data here. There's a lot of information here. What people usually do is they'll take, well, how many words did you learn at the 5th trial? And that's our indicator of cognitive performance, which just breaks my heart because there's so much information here that we could use. How could we use it differently? Well, let's fit a growth curve model to that learning task and capture people's memory span, their ability to remember a word list performance at first presentation, the number of words they're able to recall after hearing the list 5 times. So this variable here is a latent variable, but it captures individual differences in ability to learn new information. I've got some latent difference score factors here that are capturing differences between the number of words learned and the recall task performance, differences in the number of words learned and the the list B list, and the difference in the loss in words between the delayed recall task. And all these are the variables that encode what I imagine would be clinically or substantively interesting information derived from that complex task. And here's a factor. So this non-memory items, this is meant to represent multiple different cognitive test scores on other tests that are not cognitively related. We could have a nice summary factor that summarizes performance there. And let's talk about how differences between that overall level of ability, and here I'm looking at memory span, but we could look at any other aspect of memory test performance and how that selective impairment in the memory task relates to a latent class variable, which could be a diagnostic latent class variable that's indicated by background variables, biomarkers, and producing a disease classification categorization. Wouldn't that be fun? Okay, one more slide. Here's my proposal for cognitive reserve using a multi-level modeling approach and confirmatory factor analysis. Here I'm trying to take the effect modification definition of cognitive reserve and literally programming that and implementing that in an analysis framework. Although my reserve variable is going to be a latent variable and it's going to have reflective indicators, and those reflective indicators are going to be random effects from regressions of cognitive performance on brain pathology measures. And so this is kind of a longitudinal data analysis, because to do a random effects model I would need repeated measures of cognition and repeated measures of brain pathology. But rather than regressing performance on time, I'm going to regress performance on pathology. So that's a random effect. And that random effect is now an individually varying indicator, and I can use confirmatory factor analysis to summarize covariance among those random effects and come up with a latent variable to capture reserve.
We already did this.
Awesome. Did it work?
We haven't run it. We just talked about it.
You were talking about it.
And so what the limitation is, this is
really well talking about it.
it's a cross-sectional measure of reserve, because even though it's using repeated cognitive performance and repeated measures of pathology, it's summarizing reserve over the period of time in which those repeated observations were collected. So if you wanted to look at change in reserve, you'd have to have another epoch of measurement in which you could characterize multiple observations of cognitive performance and multiple observations of pathology.
I'm pretty sure the answer is no, go home. But is there, so we know that there's a way to get multiple cognitive measures from a burst design. Is there some pathology you can be measured like multiple times over a relatively short time that's actually in these different measures are meaningful? Could you use a burst design?
I don't know about that, and definitely not the right person to ask about that. But if you're, I think you could, if you wanted, you could. Here, this random regression has got, like, I'm going to regress my AVLT total rescore at time 5 on white matter hyperintensities, and if I've got 2 measures of white matter hyperintensities separated in some meaningful period of time over which I could expect there would be real change, so that random effect is meaningful, then I've got that. But what if you could probably do a random effect model that had different types of pathologies and different types of cognitive performances if you had strictly cross-sectional data?
That's definitely a burst design. Event-related potentials, you've got hundreds of thousands of brain pathology, whatever you want to call it, data points.
I don't have to go home now.
Yeah. But you have to fit that model tonight.
My thought was there's variations on stress tests, so you can give like CO2 rebreathers in the scanner and look at blood flow. Or you can have cognitive tasks, but something needs to be you can't have brain structure as your measure of pathology then. But if you have ramping up, and Yakov showed stuff like this, where you're getting multiple indicators of how healthy the brain is under different conditions within a constrained period.
Yep.
That's like fMRI.
Yep, and that's just like Yakov's fMRI task activation studies, and I think also exciting possible reflective indicators of the reserve concept.
I was just going to say, I think the focus with burst designs has been more on getting stability of measurements versus, we see people and give them a story to remember once a year versus some kind of a repeated memory test that might be on a daily or weekly basis over a relatively brief interval. So you get a much better estimate theoretically with that. But it's not really that you're looking at you could look at the standard deviation as one of the variables that people do with blood pressure and so on. But generally it's to get a better estimate.
Yeah. My interpretation is there about practice and retest effects. And so one of the keys in your designing your longitudinal study is you want to space your observations over a period of time where you expect there to be meaningful change. If I tell you you need 3 repeated observations to do longitudinal data analysis, and you're like, okay, I'll do my MMSEs at month 1, month 2, and month 3 and do my cognitive aging study, that's just not going to work out. We need to have meaningful change. And that's Laura and Van Bell's paper from 1983. What was that paper? Do you remember that paper? You guys wrote this paper. You need meaningful time interval for studying change over time. Great paper. I remember it. So, with a burst design, when you're doing practice and retest effects, cognition is changing over those repeated observations. There's real change happening. It may not be because of what you're interested in studying. It's on familiarity with the test and the testing situation, but real change is happening. But are brain changes changing over that interval? Probably not. I don't know, but I'm guessing not. So that burst design interval I don't think applies to imaging studies. Yes?
back to the one that had the multiple colors with groups. No, the previous one. Keep going. Nope. Back to it. Back. So my encouragement to people is to look at your spaghetti plots of your individual data over time. Look at your model implied trajectories for each person. And look at whether those are making sense to each other. If you only look at that mean trajectory, you can absolutely get one answer from this whole group of data with just the green line and think you've done something meaningful. But you may be missing groups of different trajectories that make more sense. And yeah, there's a mean trajectory overall, but there's a mean trajectory for the fast group and the slow group, and that is also in the same data at the same time as that mean trajectory. And I think it's very easy to sort of jump to the final answer of what the model is saying without thinking about, are there people in here who are not as well fit by this model? And I just encourage a lot of going back and forth between visualizations of individual trajectories and model suggested trajectories.
And I would add to that, look at your model implied trajectories and your observed trajectories over multiple different time scales, because if you could have a situation where change is nonlinear with respect to age, but if you use time and study with age as a covariate, it may be linear within that time and study. But then as you look at your trajectories, they're all over the place. Why is that? Well, if you plotted it over age, you might see that it's nonlinear and that all people may belong to one population trajectory, but it looks like they're in a different population trajectory because over the population, it's nonlinear. So it's never easy.
So you can always find a mean of a population. And if it's the overall group is your population, you can find a mean. But what's really interesting to me is the heterogeneity around that mean. And this, I think, kind of gets to what Paul is saying. What I'm really interested in is understanding why some people are below that mean and why some people are above the mean. And I guess the problem I have with growth mixture modeling is when you look at a spaghetti plot, you can always, say, okay, here's a group of people that kind of, are up the upper part, and you can see a middle part and a lower part.
Yep.
And this is just kind of saying what seems to be pretty obvious, and I think it's more useful to actually look at variables that explain why people start at different levels and decline at different rates. And you can do that in the same analysis. But this kind of visual analysis should be the first step.
Yeah, I agree.
Yeah.
That was my question about timescale. You answered it already.
Okay.
Whether we should use age or time.
I've been all over the place in my career, but I've settled on time and study with age as a covariate as the preferred way.
That's how you would look at the data?
But no, I would model it, time and study, age as a covariate, but I would plot it any way I wanted to and present the prettiest picture and explore it multiple different ways. Yes?
I have not heard the word Bayesian in terms of structural equation modeling. Is there a role for Bayesian inference?
Bayesian in structural equation modeling.
Straightforward stuff in many ways.
Yeah, I tell anybody who I meet that we'll all be Bayesians in 5 years. I've been saying it for 20 years now. Mplus does Bayesian parameter estimation if you really want to be a Bayesian and you understand what you're doing as a Bayesian. Sometimes you'll be doing a model and Mplus will tell you, this is a really interesting model. I would love to estimate this for you. Can you please respecify it using the Bayes estimator, because otherwise I'm going to be here for a really long time. And I've read that book. What was the book? The Theory That Wouldn't Die, right? Love that book. That's about how close I am to being a Bayesian. So I'm very sympathetic. I think it's a great place for doing inferencing. I like the way confidence intervals taste after a Bayesian analysis versus frequentist analysis. But beyond that, it's really, in Mplus, it's a computational tool. You can put in priors if you know what those priors should be and improve your estimation. Paul.
Stay tuned for Friday Harbor. I've forgotten, sometime in the future. We're not going to be Bayesian IRT.
Sweet.
And there's several books to read. John Paul Fox wrote a nice one. I'm blanking on his name, but there's a few really nice Bayesian-based books. And the model that Rich had with 4 indicators of an underlying thing and 4 time points. Yep. So you could do the factor scores as one level of a model, of a hierarchical Bayesian model, and then you have the intercept and slope on a different level. And the advantage of doing it that way is that the error is propagated through all levels of the model. It turns out to be really the same as this, but sort of written in a different way and really explicit about the hyperpriors and stuff like that. And that was me doing my fancy, I'm a general internist, but I just said hyperpriors.
You did say hyperpriors.
Isn't that cool?
Yeah, that was good.
Windows didn't break. So we're a little over time. And in my role as cheerleader, I think we should all thank Rich for having us.